Hello, good morning, good afternoon, and good evening. And welcome you to this World River and Delta System Source to Sink webinar series. Today is our Source to Sink webinar 2021-07, number 7. So we invite Professor Kevin Schaefer from the National Snow and Ice Data Center come here to talk about the Yukon River. Particularly and the impact of the global warming, how about the water quality, and he will specifically focus on mercury concentrations on the Yukon River. So before I introduce Kevin, I would like to mention next week we have 2 more wonderful talks are coming. So first Wednesday is Tom Bianchi will talk about the carbon in the delta front estuaries. And also Ella from Egypt, he will talk about the now river delta, particularly with the human impact, environment change, sea level, the delta subsidence, coastal erosion. So Kevin from currently the professor, the Snow and Ice Data Center in University of Colorado Boulder. And as you can see, Kevin working on NOAA, working on the University of Colorado and the National Snow and Ice Center. And also earlier his work, he also served, in the NASA program manager and also even a working group for the White House. So it's very, very rich. I guess he maybe will mention a couple of things. And one thing I want to point out, he received many great award like editor citation for excellency in reference and Smithsonian Computer World Award and all those. So I don't want to read all of them. And also Kevin is the lead organizer of the North American Carbon Program. And he's currently trying to understand the strength, timing, dynamics of permafrost carbon feedback. As we all know, in a high latitude area, the permafrost carbon feedback is an implication of the surface warming. It's a result of global warming, how much of the CO2 or methane could be released because as a result. So I think we are looking forward to his talk today. So Kevin, now is your turn. Please share your screen for the presentation mode of your PowerPoint.
All right, well, thank you very much. I really appreciate that introduction. Today, I'm going to talk about the impacts of thawing permafrost on mercury concentrations in the Yukon River. Oh, here's my crew. The basic question is there's a huge amount of frozen mercury in the permafrost itself. And the question is what will happen if the permafrost thaws out in the future? And, Paul asked me to put in a little bit of background here, and I did. I didn't realize he would go over it himself. But anyway, I graduated with an engineering degree, and I started working on the space shuttle way back in the day. And then I switched to the space station and eventually became program manager of the space station. And after that, I was a program manager in charge of data systems at NASA headquarters. And I did a stint at the White House. Then I went back to school. I went to Colorado State University, got a PhD, and then I worked for NOAA. And during this whole time, basically, I studied the carbon cycle on a global scale. But after NOAA, I started to focus a bit more. I went to the University of Colorado and basically focused on carbon in permafrost. I studied the permafrost carbon feedback, do a lot of studying and modeling of permafrost dynamics. And recently I've been working on mercury in permafrost. Oops, wrong direction. Lately, I have been also doing some consulting with a private company who's building CubeSats. So that's an interesting throwback to my engineering days. Now, what exactly is mercury? Well, it's a heavy metal. It's a liquid, often at room temperatures, and it can be gaseous. It's a naturally occurring element. People don't always realize this, but it's been naturally occurring since the beginning of time, leached from bedrock or emitted right into the atmosphere from volcanoes. Also, it's a pollutant from the burning of coal, this making of cement or smelting of metals, and that's released into the atmosphere. Now, the form that's most toxic to people is methylmercury. This is an organomolecule, and it's produced by microorganisms during the decay of organic material, and it tends to bond to certain proteins in the human body. And so it's toxic. It tends to accumulate in the food chain. Now, I want to talk about mercury in the Yukon River, but before I do that, I'm going to have to go into a little bit of background on what exactly is permafrost and how mercury got into the permafrost in the first place. A little background on permafrost. Permafrost is permanently frozen ground. It's defined as ground at or below 0 degrees centigrade for at least 2 years consecutively. The active layer is the surface layer of soil that thaws in the summer and then refreezes in the winter. This is a map showing the distribution of permafrost across the high northern latitudes. It covers about a quarter of the land surface in the northern hemisphere, so it's quite extensive. It's divided into various zones. Continuous permafrost occurs under 90% of the land's surface. Discontinuous permafrost occurs under 50 to 90% of the land's surface. And you may ask, well, why would that occur? Why isn't it all uniform? Well, you can imagine in your mind a hill, and on the south facing side of that hill gets sunlight. And on that side, the permafrost won't form because it's got heat. On the north side, though, it's in shadow, and you might see permafrost form on the north side of the hill, but not the south side. And so you get discontinuous permafrost. Now, here is a very typical profile of permafrost. Before I dive into it, when you see pictures like this, on the upper left, you see a map of Alaska with a yellow dot, and that shows the location where the photograph that you see has been taken. Now, this is taken right outside of Barrow, Alaska, and it shows a very typical profile. You see up here at the top, vegetation, moss, lichen, and a thick organic layer. Looks very black here. And underneath that, there happens to be a layer of fine silt. And then if you look, you could see the bottom of the active layer is a line of frozen material. And underneath that, it's frozen. And here it looks like it's weeping because it's thawing out because it's supposed to air. But that's what permafrost looks like. Now, in permafrost, the water acts like cement. And so when the ground is frozen, the permafrost is really hard, it's solid, it's resistant to erosion. And to illustrate this is a colleague drilling a core sample, and he accidentally froze his drill bit into the permafrost, and he had to go to town to get a jackhammer to get it out. Now, as you might imagine, that the drill bit did not take this lightly. He probably would have done better just to leave it into the ground. But I too have frozen drill bits into the permafrost, and they are hard to get out. So when the permafrost is frozen, it's really solid, really stable. But when it thaws out, the ice changes to water and the permafrost changes to mud. And a lot of changes happen. So when we see warming at the high northern latitudes and the permafrost starting to thaw out, we're seeing some really big changes to the ecosystems and the infrastructure up there. For example, there's all sorts of lakes up in the high northern latitudes. That's because permafrost is impermeable. And so whatever rains, the water just sits right on the surface and stays there. However, when it gets warmer, it thaws underneath these lakes, and eventually it thaws right through the permafrost layer. And what happens then is these lakes drain from the bottom like pulling a plug out of a bathtub. And that's what you see in the upper left here. Now on the lower right, you see, permafrost tends to have large amounts of ice in it, sometimes much more than the pore space of the soil. And if this ice melts out, the ground collapses, and there's a lot of change here. And this is a picture of what's called a pulsar. You can see the ice there. It's a big blister of ice, and it's melting out, and you can see the ground is just tumbling down, and often with this, there's a lot of erosion, there's a lot of change. This is pretty big. Oh, and in the background there is the Alaska pipeline, which takes oil from Prudhoe Bay down to Valdez. But it's not just the ecosystems that could be impacted, it's the infrastructure itself. On the upper right here is a building, an apartment building in Russia. And what happened is the permafrost, these buildings assume nice, solid, stable permafrost, like it's bedrock. But if it thaws out, the ground becomes unstable and the building tends to collapse. And in this case, the building collapsed within 72 hours of the first cracks that appeared. Now, admittedly, this could have been caused by bad building practices, but in the future, if the permafrost thaws out, this is the kind of thing you would expect to see. Now, in the lower right, that's actually a town called Shishmaref, and on the Seward Peninsula in Alaska. And what happened here is the ice from the ocean is retreating. And what happened is there's waves coming in, and the waves eroded all the permafrost, and the entire town collapsed into the ocean. Now, this is a pretty dramatic example, but it happens that there are villages all across Alaska where along the rivers or lakes where it's starting to erode, and the towns are literally falling into the rivers. And so there's some disruption going on up there. And to illustrate what's going on right now with permafrost, you probably heard that climate change is hitting the high northern latitudes first and hardest. And that's because of what's called the snow albedo feedback. You can imagine when there's snow on the ground, it's very reflective. But if you warm it up just a little bit, the snow season gets a little bit shorter. And the albedo changes from really bright white to basically black. And this amplifies the warming. And so the high northern latitudes are experiencing a lot of warming. Here's a map of Alaska, and I got labeled here in different colored dots, boreholes. Now these are very deep, 200 meters, so boreholes, and you drill down in there and you put a string of thermometers down and measure temperature over time at different depths. Now these are temperatures at 20 meters depths. And what you see here, the color coding, roughly the further north you get, the colder it is, which is exactly what you would expect. But what you're also seeing is that virtually every single borehole here is showing a positive trend in temperature. Even the most southern borehole down at Gulkana is showing a positive trend. It's less because it's right near zero. Now, physically, what's going on, the whole permafrost is warming up. It's just taking a long time to do it. Nothing happens really fast in permafrost, but you can imagine, the permafrost will stay exactly the way it is until it hits that 0 degrees centigrade. And then you get really radical physical changes, and that's the tough point. But we're seeing warming at all locations in the high northern latitudes. Now, that's background in permafrost. Now let's talk about permafrost carbon. Now, I think everyone's seen or heard of animals like mammoths, like this one here, being frozen and then thawed out and taken out of the permafrost and preserved frozen. But it happens that there's a ton of organic material. It happens that animals are only a very small, minute fraction of that, although they're the most interesting. They're often the most interesting. Nearly all the carbon that's frozen into the permafrost is the form of frozen plant roots. And here's a picture of some plant roots that are exposed. They're 30,000 years old, and they're exposed by erosion. And you can see on the left, there's a big ice wedge, so that's why it's white. But if you look at this, you see, wow, this looks like I dug it up in my backyard yesterday. These roots are they have their original form as when they're frozen. And that's the thing. The organic material here is just frozen. It's not petrified or fossilized. It's just frozen. And so it's preserved. And here's some other pictures to illustrate. This is taken from a tunnel dug by the Army Corps of Engineers after World War II into this hillside. And you see some fascinating things here. On the left, you see 32,000-year-old grass, and this is hanging from the roof. You know, a tuft of grass just fell down in a crevice and fell upside down and froze, and it preserved the grass. You see here, that's not an illusion. That grass is actually still green, even after 32,000 years. And on the right, you see wood that's been buried and frozen. And again, this is not fossilized, it's just frozen. Now you're probably wondering, how on earth did all this, you know, organic material get frozen in permafrost in the first place? And I'm going to show a picture to explain how that happens. This is a picture of me standing on top of what's called a thermal karst, which is a collapse of ground due to the melting of ground ice. And what's melting out here is these ice wedges. You can see at the top of this photograph is my hand, or the hand of one of the guys with me, actually. And you see a nice ice wedge there, and that's melting. The ice wedge is melting, and you can see all the ground is collapsing around it. And there's a great deal of erosion, and you can see the collapse here is about 2 to 2.5 meters. But it does expose soil profile. And this is interesting. This kind of illustrates what happens. Essentially, sedimentation at the top of the soil column buries the organic material, but the thaw depth, or the active layer thickness, does not change. And so organic material at the bottom of the active layer gets frozen into the permafrost. And you can really see that here at the very top. You see organic material with the plants and stuff, but you see alternating layers of heavy silt and thick organic material. Silt, organic material, silt, organic material. And in this particular spot, what's happened is over, 20, 30,000 years, you have episodic flooding. And when there's a flood, it deposits a huge amount of sediment right on top, buries the organic material, which becomes frozen into the permafrost. And then, alternating, this results in alternating layers of silt and organic material. Now you may be wondering, well, this is interesting, but what has this to do with mercury? Well, it turns out that mercury bonds to the organic material, and it especially bonds to sites in the organic material that have sulfur compounds with it. And so over time, and it's naturally occurring, and so over time you build up this mercury bound to the organic material, but then the organic material becomes frozen in the permafrost. And so you may have 3 meters or more thick layer of frozen organic material, and attached to that is mercury. Now what we have here is a plot showing how mercury bonds to the organic material, or the amount of mercury that you would see depending on the amount of organic material. When you have near zero mercury or organic material, let me start over. On the horizontal axis, you've got soil organic content in percent. So when you see 50%, that means by weight, half of the soil is organic material. Now on the vertical axis, you got the soil concentration, which is nanograms of mercury per gram of soil. And you see a definite trend here. When there's no organic material, you see very little mercury, which makes sense. There's nothing for it to bond to except clays and different things. But as the organic material increases, you see a strong relationship with the concentration. And what happens here is when you have very little organic material, the mercury concentration is receptor limited, meaning you need enough organic material with enough receptor sites to actually bond with the mercury in order to increase the concentration. After a while, though, if you increase the organic content, there's plenty of receptor sites, and then the mercury concentration becomes flux limited. In other words, the mercury depositing on the surface determines how much is actually in the soil. There's plenty of receptor sites. And you notice here, very different regimes. The receptor limited regime is nice and tight and linear. And then when you get into flux limited, it's very noisy, reflecting a lot of variability in space and time and flux up to the ground. So one of the things we did first, before we studied mercury in the Yukon is we tried to determine how much mercury was actually frozen in the permafrost. And to do this, we drilled permafrost cores. And this is a picture of the equipment we had to use. Nice heavy steel. This was really hard to lug around in the tundra, I can assure you. And what you do is you drill the cores. And here's the pictures of us drilling cores. You drill the cores, you wrap them up, and then you put them in a freezer, which we powered by a battery or by the truck or a generator. And then you take them back into the lab and you slice them up, slice and dice up the samples, the frozen permafrost samples. Then you dry them out and you measure the amount of organic material, and then you measure the amount of mercury. And these are the results of what we did. We did 13 cores in a rough transect from north to south through the entire state of Alaska. And what we have here in black on the horizontal axis, you've got the ratio of mercury to carbon. So micrograms of mercury per gram of carbon. And our measurements are in black, and we see a nice peak around 1.6 micrograms per gram. And we compared this to the other measurements that were made in the lower 48 states. And we see pretty much the same distribution. So what we did is we took a map of carbon content in permafrost and multiplied by the median ratio of mercury to carbon, and that produced a map of mercury in permafrost. Now you can see the color bar here shows different amounts of mercury. It's in micrograms per meter squared, so it's total column mercury here. And you can see in the middle that this goes to 0 to 300 centimeters. In other words, down to 3 meters of depth. And you can see there's quite a bit of spatial variability here. And you probably wonder, why is this the case? Well, it all depends on how it got buried or whether it got buried at all. In places where there's high sedimentation, you get a lot of carbon buried, so you get a lot of mercury. And here I got an arrow pointing to the Mackenzie River basin, where it's heavy sedimentation. So there's a lot of carbon, there's a lot of mercury then. But in other areas where you got very low overburden, like in mountains, where that's the source of the sediment. So all the sediments have been eroded away. And so you don't see a lot of mercury there because there's not a lot of carbon. And so what we did is we took this map and put it into a model and tried to see how this would change, how much of this mercury actually stays here. Because what this represents, this is mercury bound to frozen organic matter. And in the future, it's going to thaw out. And once it thaws out, the organic matter will begin to decay. And once it decays, it will release mercury back into the environment. Now, here's a picture of the global mercury budget. In these kind of simulations, you really got to think global as well as local. And you see here, up on the left, these are the largest reservoirs. The active layer, that's the surface layer of soil in permafrost regions, and the amount that's actually frozen. And then you see all the other soils for the entire planet. And vegetation is actually fairly low. And then, of course, the ocean is a fairly large reservoir in aqueous form. The atmosphere doesn't hold that much either. But you notice here that permafrost regions contain twice as much mercury in the soil as the rest of the globe combined. So there's a lot of mercury there. These are just measures of different fluxes to and from the various reservoirs. The thing to notice here is on the far left, the anthropogenic emissions. Now, these come from the burning of primarily coal, but some oil. And I just wanted to remind people that there's a reason the mercury is actually in the coal itself. It's the same reason why we have it in permafrost. It binds to the organic matter and builds up over time. It just happened that coal, it didn't decay, it changed into coal, but the mercury that was originally bound to the organic matter is still there. And that's why when you burn it, it gets released back into the atmosphere. It's like short circuiting geology there. Now, what's going to happen in the future? There's a lot of people who run lots of climate models to try to estimate what will happen in the future. And the horizontal axis here, you got year, and this happens to go out to 2100. And on the vertical axis, you got temperature change from pre-industrial times. In this case, they define pre-industrial right around 2000, but you get the idea. They run a bunch of scenarios, and each scenario represents a vision or a possible future of burning of fossil fuels, depending on what you assume for the economics and social response, et cetera, et cetera. And that scenario there, the blue one, is the scenario if you stopped all emissions instantaneously right now, and you'd see a temperature go up and then stabilize. Now it happens that the Paris Accord, we have a global treaty called the Paris Accord, which the goal is to limit global temperature increase to roughly 2 degrees centigrade. And so this scenario is the scenario that's closest to the Paris Accord target, and that's called RCP 45. Don't ask me what the acronyms mean, but that's the acronyms we use. This high scenario here, that's the scenario of unconstrained burning of fossil fuels. But it's interesting that when people thought up of this particular scenario, they thought this was the least likely of all scenarios to happen and was considered an end case. It happens that right now we've already greatly exceeded this scenario. And so we're on a track that's higher than this scenario. So what I did is I took these scenarios and I forced my model with them. And this is an illustration of what we project to happen to the permafrost for the unconstrained burning of fossil fuels scenario, which we call RCP 85. On the left is an animation of active layer thickness as a function of time. And what you see here is that as it gets warmer and warmer, the colors get redder and redder, which means the active layers, it's thawing down from the top, the active layer is getting deeper. But also what's happening is the amount of permafrost is getting less because it's melting from or thawing out from the south to the north. So the permafrost is thawing from the top down and from the south to the north. And on the right is a simple plot showing the total permafrost extent. On the horizontal axis, you got date. And on the vertical axis, you got area in millions of kilometers squared. And you see, it starts out flat. And then for the RCP 45, which is close to the Paris Accord, you see, there's some thawing, then it stabilizes and stays constant. But for the RCP 85, which is the unconstrained burning of fossil fuels, you see that you get a decrease of permafrost. You lose about 85% of all permafrost, pretty much saying it's going to completely thaw out. Now, I notice here that a lot of climate projections, they kind of end in 2100, but here I go out to 2300, and that's because nothing really happens fast in permafrost. It's still cold up there, even though it's warming up and the permafrost is thawing out. So it just takes a long time for the permafrost to react. In fact, just so you know, the little ice age in the 1400s, the temperatures of permafrost are still reacting to that. So it takes centuries for things to happen in permafrost areas. Now, this is estimates of mercury flux to the atmosphere. It's in the form of elemental mercury, Hg0, gaseous elemental mercury, metal. On the horizontal axis, you've got year, and we start this at 1900, so you can see the current or recent date time, and it goes all the way out to 2300. And on the vertical axis, you've got the flux to the atmosphere. Now it starts out as 0 because we assume a kind of equilibrium, that has built up over tens or hundreds of thousands of years between deposition and release. So there's a balance that stays roughly constant. But you can see roughly 2000, permafrost starting to thaw out, and the amounts are getting higher. And you see the blue line, which is the scenario close to the Paris Accord. Yeah, the emissions increase, definitely. but then they stabilize, and they're not that much. But you look at the unconstrained burning of fossil fuel, RCP85, and you see they really start to increase. And they actually, I put a line on here as a reference. That's the current global anthropogenic emissions of permafrost. So what you see here is large scale emissions comparable to anthropogenic emissions, but persisting for centuries. And there's a key difference here. Anthropogenic emissions, they come from burning of, like coal. Well, you can go to that coal plant and you could, control how much mercury gets emitted. And we've been doing that for a very long time. There's a lot of constraints on how you do that. But for permafrost, what you have is highly diffuse over millions of square kilometers releases. You cannot control it at all, and it will persist for centuries. So this represents a huge global perturbation to the global mercury cycle. But today, finally, we're getting to the Yukon River. I wanted to see how it would change in specific river basins, and we focused on the Yukon River. Now on the left here is a map of Alaska, and you can see outlined in red the drainage basin for the Yukon River. It drains off of the Yukon-Kuskokwim Delta in southwest Alaska into the Pacific Ocean. And the white and blue represent, the boxes represent our modeled projected losses of permafrost or losses of mercury due to thawing of permafrost and the decay of the organic matter that was frozen. And you can see here for the RCP 4.5 scenario, and the units here are milligrams of mercury per meter squared. So it's a total column loss of mercury. And you see most places it's actually really small, near zero. And that's because for this scenario, those areas don't thaw out all that much. The areas that thaw out are mostly along the southern margins of the permafrost domain. And so you can see in the Yukon River, what's really thawing out is the permafrost at the lower end of the drainage basin near the mouth of the river. So it's not that bad. You do notice in the Mackenzie River Basin, though, at the southern edges, you do see some more there. So the increases are a little bit higher in that basin. You go to the RCP 8.5 scenario. This is the unconstrained burning of fossil fuel scenario. And you see widespread releases of mercury or losses of mercury. And this is due to the fact that under this scenario, you have widespread broad-based thawing of the permafrost, and followed by the widespread decay of the organic material that was frozen. And so you get a lot of releases here. And you can see, again, areas that have the most carbon now are the areas with most erosional deposition. And so you could see, for example, in the Mackenzie Basin here, there's a lot of buildup because there's a lot of organic material that's been buried. And the same is true for the Yukon right here. But you notice along the northern edges of the Yukon drainage basins, that's the Brooks Range. And so those are big mountains. There's not a lot of buried organic material there, so there's hardly any losses. And so this is reflecting the pattern both of large-scale thaw and amount of frozen material. So now let's take a look at the Yukon in detail. Now, on the left here, we have the export of mercury, aqueous mercury, by the Yukon River. On the horizontal axis, you've got date out to 2300. And the vertical axis, you've got the export in megagrams of mercury per year. So this is all, exported right into the Pacific Ocean. And you see the dots there represent observed values. People have actually observed this. And our model is looking pretty good. We got a big uncertainty bar, but we fall right in the middle of the observed values, which is very encouraging for a modeler, I'll be honest. For the RCP 4.5 scenario, which is close to the Paris Accord, what you see is a slight increase in the amount of export, consistent with minimal thawing of the permafrost. And it stays constant. It stays roughly close to what we're observing now. This is good. But you look at the RCP85 scenario, which is the unconstrained burning of fossil fuels, and you see this massive increase. You see a tripling of the export of mercury just by the river. This is not good. And this, because nothing happens really fast in permafrost, this persists for centuries. Even though I stopped this in 2300 because I ran out of computer time mainly, but this would persist for a couple more centuries. Now let's take a look at the concentrations. This is more important for a human health viewpoint, you might say. And here we got the day of year on a horizontal axis. So we're representing a typical year or a year in the life of concentrations. So we got day of year, it goes from 0 through 65 on the horizontal axis. And the vertical axis, we got mercury concentration in nanograms per liter. And we got 3 lines on here. The black line is what we simulate today. And I didn't show it on here, but it's right smack in the middle of what's observed. But what you see is the first part of the year, it's really, really low concentrations. And that's because the river is basically frozen. But then you see a spring thaw or melting of the river and a huge flush. Basically, this is the snowmelt flush, the peak snowmelt. And you see the concentrations. The water flow, of course, peaks, as you might imagine, but any mercury that's built up over the winter just gets flushed out. And so you get a peak in concentrations. And then over the summer, it stabilizes and then slowly decreases. And then in the fall, you see the river starts to refreeze up and the flow goes down, and so does the concentration. For the RCP45, which is the blue line, we see, we see increases in concentrations, but not a heck of a lot more than what we have right now. However, you see for RCP85, the unconstrained burning situation or scenario, the concentrations basically double or triple. And this is not good. Now, I put a line on here. The EPA no longer uses this criteria, but it's the criteria for clean drinking water. This is what the EPA says is the maximum limit of mercury in the water. Now you notice here, the concentrations right now already exceed the EPA criterion. Now it's interesting, you got to realize that we've been burning coal for 150 years now. And when we burn the coal, we release the mercury. That's mostly been in the lower parts, the lower latitudes. But over time, the mercury has drifted. It's gone into the plants, been released by the plants, and just kind of hopped north, north, north. And now we're seeing a lot of perturbation to the mercury concentrations in the high northern latitudes. And this is from the cumulative effect of burning coal and smelting ore for the last 200 years or 150 years. And so already people are very concerned about mercury in the high northern latitudes. What we're seeing here is where we should be even more concerned, because if we thaw out the permafrost and release the frozen mercury, it's just going to get a lot worse. Now, the last thing I wanted to touch on is how would this affect the mercury concentration in fish? Fish is a staple food source in the high northern latitudes, but also there are large fisheries. There's people take fish out of there, sent out all around the world. This is from a model again, and on the horizontal axis you've got date out to 2300, and the vertical axis you've got the mercury concentration in fish. Now this is micrograms of mercury per gram of fish wet. What that means is, the fish meat still has water in it. There's a lot of measurements where they dry the fish out, and then it'd be micrograms per dry mass. Anyway, you can see here I put an observed range. There's a wide range of observed values in fish. but the mean is slightly lower than what we simulate, but what we simulate is still pretty realistic. And I put on here the EPA criteria for the maximum amount of allowed mercury in the fish. Now you can see the blue line represents close to the Paris Accord. Yes, the mercury on average increases in the fish in our model, but it doesn't actually violate on average the EPA criteria. This is okay. However, you look at the unconstrained burning of fossil fuel scenario 8.5, and you see that the concentrations more than double over the next 100 years. And they stay that way because the source of the mercury is just continuing to come out. This indicates that this may be a risk to our food supply. Now, exactly how much of a risk and what that might mean, I did not cover because that involves epidemiology and human health research that I did not do. All I can say is that if you thaw out the permafrost, you're going to increase the amount of mercury in the food supply. That's all I wanted to talk about today. I wanted to thank you all for letting me speak. I really appreciate it. Thank you. And if there are any questions, I'll be glad to answer them if I can.
Kevin, thank you so much. And this is such a very, very interesting talk. I learned a lot because I mainly focus on low latitude river and the delta, but this high latitude environment with the rapid global warming, and it's something we really, really need. Thank you so much. And particularly the permafrost, such a wonderful natural sediment storage lab. Is a freezing condition, because as we all know, the people get a sample from Amazon, from any other river system, had to ship into the lab and freezing. But now your working place is naturally freezing all the time. So this is why you show the 32,000 years, the very good carbon preserved so well. And so I guess many biochemical scientific colleagues have some questions, but I have a quick question first. And sure. So you see the mercury, so far we don't need to worry about to the fish, like the salmon or something. But how about to the crab, like a lobster or king crab, we are eating? And also, if those is less impact, how about the near shore, near the river mouth, the shellfish? I guess there's a lot of concern about that. Is that right?
It's all possible. I have not studied shellfish or crabs. Mm-hmm. However, you can imagine that if it enters the food supply, food chain, it will end up in both of those. How much, I cannot say. But you think about it, the way it happens is you leach out organic material from the ground, in terms of dissolved or particulate organic matter, and along with that is mercury, and the microbes eat that, and then the plankton eats the microbes, and then the fish eat the plankton, and you see it builds up, and if the crab or the shellfish grabs the same organic material to eat, it will also accumulate. Now, I can't tell you exactly how much. I'd have to dig into that. Yeah. But I'll think about it. But the crab, that depends on how much is in the ocean. Sure. Unless I'm primarily looking at the freshwater food chain right now.
That would be very, very interesting. Okay, let me see. Okay, now Tom, you can unmute yourself.
Hi, Kevin. Very nice talk, very comprehensive, nice history of the Mercury story and permafrost. I have two quick questions. One is the idea that the mercury is presumably or predominantly bound in organic carbon. I'm wondering, as you look across much of the Earth's surface, how much variability there is with mercury binding to different types of minerals in different regions of the world, and what that might mean in terms of the release of mercury, you know, from different regions. That's one question. And then the other one is when you talk about the resistance of permafrost taking many centuries to respond, as it has in previous with previous changes in global climate. Is that assuming, so that assumption for the future with these models, these RCP models and so on, is that assuming that the response of permafrost to warming is linear or going to be non-linear?
Well, the first question about bonding to minerals. Mercury can bond to minerals, primarily clay minerals, because the clays have lots of surface charges, lots of potential receptor sites. Once it bonds to that, it tends to be much more stable than bonding to organic matter, because the organic matter is vulnerable to decay by microbes, whereas the clay is not. Now, I don't have an exact answer to how much bonds to the clay, but there is a bonding to clay. And in fact, if you think about this, it's part of the natural background cycle, the really slow geologic cycle. Of course, it bonds to the clay, and the clay becomes a rock eventually. And then sometime in the future, the rock erodes and puts the mercury back. So that's the geologic time scale kind of thing. Now, the second question was, is the response of permafrost linear or nonlinear? And the answer is it's nonlinear. And the way we represent it, we actually use full physics models of soil temperature and moisture to represent this. And so those responses are actually nonlinear. So yeah, it's nonlinear. And what'll happen is, the way to think about it is, the frozen soil, the permafrost, absorbs energy from warming and slowly warms up, and diffuses the energy vertically in a diffusion type process. And then it hits 0 degrees centigrade. And then there's some radical changes. It changes phase, and a whole bunch of things take over, and those processes are also nonlinear. So it could get a little complicated, but the way to think about it is like broccoli in your freezer. As long as it stays in the freezer, the broccoli stays broccoli. But you take it out of the freezer and put it in the fridge, it eventually thaws out and decays. And that's the kind of process that we're actually representing, a very simplified view of it. Is there any other question? There's a Robert Aller. Yeah.
Yep, that's me. I'm very nice presentation. Thank you so much.
Thanks.
I was curious as to how you determine the product speciation as you release the mercury from the permafrost. Presumably, as you mentioned, it's volatilized to some degree. It ends up also in solution to some degree, and presumably some of it says methyl mercury. And I'm curious as to how in your models you constrain the speciation patterns in the different regions of the drainage basin.
We actually try to represent as many pathways as possible. And yes, we represent 3 main mercury species. One is Hg0, which is atomic pure mercury. The other is Hg2, which is a +2 ion, and then methyl mercury. And we actually differentiate between those 3 species in the model. And most of the deposition is Hg0 and Hg2. We based on measurements, we split the fraction of that. And then we got more than one uptake pathway, but predominantly the biggest uptake pathway is when it deposits underground. It just bonds to the organic material there. And that's, once it's bound, we treat it as Hg2. And then when it decays, it gets released either as Hg2 or Hg0. And Hg0 goes up into the atmosphere. The Hg2 tends to get recycled. We represent leaching of carbon into the water, and we represent the decay there. And then we use, say, observed ratios of mercury concentration in water to mercury in fish, and that's how we estimate the fish. So we try to represent all the species. I must be honest, there are definite improvements I can make there. And I'm hoping to get funded to do that very thing and increase the number or variety of pathways, get better constraints on physical constraints on what those mean and how fast they change. So that's
part of my wondering about this is not just the chemical aspects or the decomposition aspects, but as you showed, the permafrost, as it's being thawed, you get a variety of different sort of small scale topographies and in the permafrost and ponding and so forth. And I would imagine that if you have ponds and shallow pools on the permafrost, that the patterns of speciation that result from decomposition pathways would be very sensitive to that. You get more or less methyl mercury, for instance. And so.
Yeah, we try to represent that, but I must be honest, my representation is rather simple. Mm-hmm. There are other models that go way deep into the aqueous chemistry of mercury. We just have a lake fraction and amount of aqueous material mm-hmm. and some very simple chemistry. That's all we can afford actually right now on a global model of this scale. Mm-hmm. We're constrained by computation time, so we have difficult choices.
Yeah.
But I'm hoping to improve that kind of representation, the aqueous chemistry and the food chain accumulation.
Yeah. Great. Extremely interesting. Thank you so much.
Anybody else? So Kevin, how about the nutrient? So because with more and more that kind of permafrost soil melt down and vegetation landscape change, so we expect to see more nutrient in the river water?
Yes, my model doesn't actually represent nutrients, or it does so in an extremely simple way. The nutrients you're talking about, they're most important is nitrogen. And yes, when the organic material decays, it will release nitrogen, which will promote growth. Mm-hmm. It happens that these ecosystems up in the high north, they look very green, of course, but they're actually nutrient limited. A lot of times the growth is limited by the amount of nitrogen. Mm. So every bit of nitrogen that comes from decay is used up. And this also makes sense in the decay of organic material is really slow mm-hmm. because it freezes each summer, freezes each winter, and it just takes, the characteristic decay time is 75 years. So once it's locked in, once the nutrient is locked in the dead organic material, the live organic material is nutrient starved. But I hope to include nutrients in the model in the future to see how that affects it.
Interesting.
There is a question on the chat about sending the reference that showed the green grass. I'm going to have to dig that up. There is a paper, I just don't remember it off the top of my head, but I do know they measured that using basic carbon-14 measurements.
Why not? Anybody else? So, yeah, Joe, Uncle, go ahead.
Hi, Kevin. Great talk. I've got a question about your model projections and how they might correspond to the reduction of methane emissions anthropogenically from the Minamata Convention, and whether the release from permafrost might offset any of the reductions that we're planning over the next few decades.
I'll have to dig up the numbers, but I have not compared the simulated methane emissions to the global anthropogenic emissions. I'm sorry, but we do simulate the methane emissions, and to give you some rough numbers, the when you thaw out the permafrost and release the or decay the organic material, you release methane and carbon dioxide. And we estimate that by 2300, that will contribute to warming by about 7%. And that represent, out of that, I think roughly half of that is from methane. But the amount of methane is on the order of 2% of total emissions, which is consistent with what you would expect on a global scale from wetlands. And by that, I mean, total carbon is X, 2% of that or so is methane. And so that'll give you an idea of how much methane we expect. You can look at your methane budget and estimate that.
Yeah, I was thinking more about the mercury emissions. So the Minamata Convention.
Oh, the mercury. Oh, I thought you were talking about methane.
Yeah,
all right. I was answering the wrong question. Okay. Yeah. This, if our projections hold true, this will blow that completely out of the water. This will be a very difficult challenge.
I guess that's a huge issue. I mean, it's obvious to say it's a huge issue, but a lot of effort, I think, is being taken to try and reduce mercury emissions anthropogenically without much consideration of this kind of natural and kind of mobile mercury source that is going to become more important under climate warming scenarios. Yes,
yes. And one of the reasons for that is this is in past global mercury budgets, there's been a broad assumption that there is no mercury in the high latitude permafrost regions, or very little. And these budgets only consider soil to 30 centimeters down. So, this much. But in permafrost regions, the organic material frozen extends to 3 meters and in some cases down to 40 meters. So it's a lot of organic material, and our measurements clearly indicate that it contains mercury. So it's a pool that people forgot. And so now people are looking at this, and ours is the first projection of what might be released. And I'm pretty sure that others are working on this as well. Different models will yield slightly different results. But yes, that's why I put in the current anthropogenic emissions. The emissions from the permafrost are at comparable in magnitude to current anthropogenic emissions, and we're having a hard time getting those down. But the emissions from the permafrost, you cannot control because they're diffuse over vast areas. And yes, this will perturb the global budget. So what is emitted here will eventually end up in the lower 48 or lower latitudes, just like what was emitted in the lower latitudes has eventually ended up in the permafrost regions. The reverse is also true. So yeah, this is a big risk to the convention.
Thanks very much.
So Kevin, thank you again for this wonderful, interesting topic. And as the Source to Sink community, we know in the last 40 years, many research study have done in the low latitude tropical river system, like all the way from 1980s Amazon to the Mekong to the Fly River in Papua New Guinea and to even New Zealand and the Irrawaddy and Ganges, Bumaputra, all those. And but we can put something on the record. I think next decade, maybe 2 decades, there's more and more focus could be shifting to the high latitude, like the Yukon River. It's relatively many unknown, like a Mackenzie River, like the New Greenland and Siberian, the Russia River systems. And so, Kevin, if you know somebody can talk about the sediment, we want to know how much the sediment changed in the Yukon River or organic carbon to the sea. So please let us know. We want to invite them to give a talk.
All right, sounds good. I do actually know someone. I'll send you an email.
Yeah, we definitely need it. As I mentioned, I think next decade will the shifting to all the way from tropical to the high latitude. river systems. And also next week, again, you know, next Wednesday, Tom, you know, here, and also Allah from Egypt will give 2 wonderful talks. Please mark your calendar and come back. So otherwise, Kevin, thank you very much. And thank you for those audience. This talk is will be recorded on the YouTube, available for your rewatch. Okay, thank you very much.
Thank you very much for letting me speak.